Welcome to today's video. Today we're going to talk about Green's integration theorem. So that is 15.5. Green's integration theorem. Now, you will have noticed that we have introduced basically two very different notions of integration. We have talked about volume integrals in the first part, and we have talked about line integrals over scalar fields and vector fields in the second part. We have treated those as completely disconnected for now. So, of course, a question would be, is there a connection between those two notions of integration? Geometrically, that would mean something like, is there a connection between the volume of a body that would be computed using the volume integral, and in 2 dimensions, the circumference of a body? So are these connected in a certain way? And from geometric intuition, you would say there should be a connection, at least for some cases. But how exactly does that work? And that is what Green's theorem will provide us here. So basically, the question is, can we somehow connect these two ideas, these two notions of integration? So, as I said, we have developed two different notions of integration. Specifically, volume integrals and line integrals. So the question is there a connection between those? For example, in R2, so if we're talking about 2-dimensional integration, is volume and circumference of a body connected? And you know it's not directly connected, but maybe the function, the vector field that we integrate, provides some kind of connection for those two. And this connection is provided by Green's theorem, and it's important to note that Green's theorem only works in dimension 2, actually. So let's write down that theorem first, and then we can see how it's going to be applied. So that's Green's theorem. We start with the domain. So as usual, let D be the domain, and this time we need a domain in R2. We want it to be open because we want to apply differentiation. And we need a vector field defined on D. V D to R2 is a vector field, and that is continuously differentiable. Furthermore, let's talk about the set that we are interested in. So we don't want to integrate over the set D, but over some set that is contained in D. So furthermore, let B be a set that is contained in D, and remember D is a set in R2, so B is usually also a set in R2. So let be a compact set. And remember, compact means closed and bounded. And we want it to be non-trivial, meaning the interior of B needs to be non-empty. And that excludes subdimensional sets, so to say. So, for example, a line segment in R2 that would have empty interior. So things like that are excluded. So we need a set that really has dimension 2. And now we look at the border circumference of that set. And we want that border, we want to use that in our computations. That means we need to be able to describe that border as differentiable curves. And we want those to be finitely many curves, and we want them to be closed. So let the border of B consist of finitely many closed and piecewise differentiable curves such that B lies to the left of these curves with respect to the direction of traversal of the respective curves. Okay, so what I mean by that is we are in the plane, so there is a notion of left and right. And if we have a curve, then we're moving along that curve. So here's a curve. This is the direction of movement along that curve. So then this here is left and this here is right. Yeah, so if you're moving along that curve in the direction of traversal, then there's a left and a right. If we use the direction of traversal like this here, yeah, now you have to kind of turn around and again look into the direction of reversal. So you're moving from the top to the bottom, and so that means for your direction of traversal, this here is right and this here is left. And of course you notice this can only be defined in that way as we're in the plane. It will become a lot harder if we're moving to higher dimensions. Well, not a lot actually, but you have to adapt the definition of being left or right to use something else if you're moving to higher dimensions, right? If you have a line in R3 and you're moving along that line, then of course you cannot really tell which is left. Is this left, or is this left, or is this left? We just don't know. Yeah, so it has to be another way in higher dimensions. But this is how it can work in the plane. And now to the theorem itself. So we have the vector field. We have that set B that is bounded by piecewise differentiable curves, closed curves. And we have defined what left means with respect to direction of motion along these curves. And of course, you can just turn around the traversal direction if that doesn't suit your needs. It's just a matter of parametrization. And then the theorem says there is the following connection between an integral, a volume integral over B, and a line integral along the border of B. And that is this here. So the line integral along the border of B over the vector field Vx ds is the same as the volume integral over the domain dB of the following scalar field. The scalar field is dv2 dx1 minus dv1 dx2 of x dx1 x2. Okay, so this is Green's theorem. And it does seem a little strange at first, but we'll see how it can be applied in a couple of examples later. Let me spend 2 more minutes to talk about how these curves for B are meant to be interpreted. So let's say we have a domain B that looks like this, for example. Just take a disk. So that's our field, that's our B. The interior is not empty, so that's a very fine B. Now what about the boundary of B? Well, the boundary of B is obviously this circle here, right? So that is the boundary of B. And so the question is, how can we parameterize that boundary in a way such that B itself is to the left of that curve? And basically the only thing we have to pay attention to is the direction of movement. So we can move along the boundary in this way, this direction here, and that will ensure that the set B itself is to the left. Yeah, if you're standing here, then this is left, this is left here, this is left here. So these arrows point to the left of the direction of traversal that we indicated by the arrows. So we just need to pay attention when we derive the parametrization of the curve, that we do it in the right way, such that the set B is to the left of the curve. Okay, one more example. We also said we don't need to have a differentiable curve, but it needs to be piecewise differentiable. So for example, if we have a set like this, a rectangle as our set B, then that's also fine. The border in this case consists of those 4 pieces here. Each one of those is just a straight line, so each one of those is a differentiable curve. But now we have 4 pieces that we need to consider. So that boundary is now piecewise differentiable. With 4 pieces. And again, we need to pay attention to the direction of traversal. We want B to be on the left of those curves, so the direction of traversal needs to be chosen in this way here. Yeah, such that, again, B is on the left. And finally, I also said there may be finitely many such piecewise differentiable curves. So let's see an example of where we need more than one curve on the boundary. And again, we'll take the most prominent example for that. It's the donut in dimension 2. It looks like this. So if that is our set B, then of course the boundary consists of this circle here and this circle on the outside. So the boundary now consists of 2 pieces. two different curves. Both are differentiable. So we just need to talk about direction of traversal. This outer one should be clear. We've seen that already. So we need to traverse that in this way to make sure that to the left of that direction we have a set B. So again, that's left of the traversal direction. Now for this inner curve, again, we want to make sure that the set B is to the left. So we want arrows like this here, pointing in the direction of B. And for that, we need to make sure that we move correctly. So the right movement here would be to move this way here and this way. Okay, so on the inner boundary, we need to rotate differently from the outer boundary to make sure that B is always on the left. And one final remark, Green's theorem can be used to compute the volume from the circumference, basically, or vice versa. The only thing you need to make sure is to choose the right vector field. So that expression here, that here is, of course, a little strange, but it means if you choose V in a way such that this is the one function, then you have a formula for the volume that depends on just the line integral. So you don't get the volume from measuring the length of the boundary, of course, but you get the volume from integrating a certain vector field along the boundary. And you just need to determine the right vector field, and we'll see how that works in the examples. For now, let's just write down that little remark here that says Green's theorem can be used for volume computations if we choose the vector field right. So Green's theorem can be used to compute the volume of B if V is a vector field with where this expression inside of the volume integral dv2 dx1 minus dv1 dx2, where this is equal to 1. Or some other constant. Yeah, it doesn't have to be 1. Of course, you could also have some other constant that you could just take out of the integral, and then you wouldn't get the volume, but you would get constant times the volume. You just need to divide by that constant afterwards. Okay, so this is Green's theorem. This is an illustration of how it works. We'll see a couple of examples in one of the upcoming videos to demonstrate how Green's theorem can be applied for computing these integrals. And I'll see you then.